Here in section 7.4, we will cover partial derivatives. Recall earlier in the semester, the definition of a derivative with respect to x of a function f of x is the limit as h approaches 0 of f of x plus h minus f of x over h. Now here, this leads to a natural question: how do we take derivatives of multivariable functions? Before I get into that, let me talk about the notation of it. Earlier, we would use dx to represent the derivative with respect to x, but that's reserved only for functions of x. Here, our functions are going to be of two variables, of x and y, so we use something slightly different. We use this, what we call a partial. So this means the partial derivative with respect to x, and this here is the partial derivative with respect to y. So with that in mind, how do we find partial derivatives with respect to x and a partial derivative with respect to y? Well, it's the exact same thing as earlier. We just take the limit as h goes to 0, and it looks something like this. The partial derivative with respect to x of f of x comma y is the limit as h goes to 0 of f of x plus h comma y minus f of x comma y over h, and the partial derivative with respect to y of f of xy is the limit as h goes to 0 of f of x comma y plus h minus f of x comma y all over h. So notice here, when we're taking the derivative with respect to x, y is held totally constant. And similarly, if we're taking the derivative with respect to y, x is held constant. So let's take a look at an example. Here we want to find the partial derivative of z with respect to x if z is given by x squared plus xy plus y squared. So we're going to use our limit definition here. So remember, the derivative is the limit as h goes to 0 of f of x plus h comma y minus f of x comma y all over h. Okay, so plugging in x plus h into the function, we're going to get x plus h squared plus x plus h times y plus y squared. That whole quantity, we're going to subtract from it x squared plus xy plus y squared. We're going to put that all over h, and we're going to take the limit as h goes to 0. So we can expand this out, and we're going to end up with something along the lines of x squared plus 2xh plus h squared plus x times y plus y times h. Here I'm just distributing the y in here, plus y squared. That whole quantity, we're going to subtract from it x squared plus xy plus y squared all over h. And that will simplify down to the x squared here and here cancels out, the xy here and here cancels out, and the y squared here and here cancels out. So it boils down to the limit as h approaches 0 of 2xh plus h squared plus yh over h. So we can factor out an h, and we'll get 2x plus h plus y over h. Now the h's on top and bottom cancel, so we're left with the limit as h goes to 0 of 2x plus h plus y, which is going to end up with just being 2x plus y. And that's your final answer. Now let me take a second and let's look back at our function. Remember, it's x squared plus xy plus y squared. So we have x squared plus xy plus y squared. Here, instead of y, I'll just plug in a constant. I'll pick 4. So we can rewrite this as x squared plus 4x plus 4 squared, which is just 16. So now let's say we want to take the derivative with respect to x of this function here. Well, we don't have to do any fancy limits or anything like that. We can just use our standard power rules, and we'll get 2x plus 4. The 16 goes away to 0. So without doing the fancy limit thing, we end up with 2x plus 4. The choice of 4 here is totally arbitrary. If we put in any number, we'll just end up with 2x plus that number. The idea I'm trying to get at here is when we're asked to take derivatives of fancy things like this, z equals x squared plus xy plus y squared, and we're taking the derivative with respect to x, all we do is treat y like a constant. Let's take a look at how that might look in action. So here we're given the function z equals 3x minus x squared y squared plus 2x cubed y, and we're asked to find zx and zy. Now this here, this z sub x and this z sub y, those are just different ways to write the partial derivative of z with respect to x and the partial derivative of z with respect to y. So we want to find the partial of z with respect to x and the partial of z with respect to y of this function. Let's start with the partial derivative of z with respect to x. What we do, like we found out earlier, we treat y like a constant, and we just apply our standard differentiation rules. So 3x minus x squared, y squared plus 2x cubed y, we can just go term by term. The derivative of 3x is just 3, minus, and then the derivative of x squared times y squared. Remember, here y is a constant, and so therefore 2 is y squared. So y squared is a constant, and we just have a constant times x squared. So when we take the derivative of that, we will end up with 2 times the constant y squared times x. Okay? And then for the last term, we have plus 2x cubed y. Remember, again, y is a constant, and so 2y is a constant as well. So all we do is we bring down the exponent, multiply by the constant in front, 2y, times x to the 3 minus 1 power is 2. So we can rewrite this as 3 minus 2y squared x plus 6yx squared. All right, let's find the partial derivative of z with respect to y. So now we're going to treat x like a constant. So if x is a constant, that means 3 times x is also a constant, and the derivative of any constant is just 0. So we're going to have 0 minus, and now x squared is a constant. So when we take the derivative, we bring the exponent down, multiply by the constant times y, and we subtract 1 from the exponent. So 2 minus 1 is 1. And then for the next term, we have plus, and again, 2x cubed is a constant, so a constant times y is just going to be 2x cubed. So this here is your derivative with respect to y, and this is your derivative with respect to x. Let's take a look at one final example in this video. We're given the function f of x comma y equals x times e to the x squared times y. And we want to find f sub x, or that's the derivative of f with respect to x, and f sub y, the partial derivative of f with respect to y. And we want to evaluate both of those partial derivatives at the point 1 comma natural log of 2. So let's begin first with the harder one, and in this case the harder one will be the partial derivative with respect to x. We want to find fx. Here we have to use the product rule because we have x times e to the x squared times y. So we have a function x times the function e to the x squared plus y, so we have to use the product rule, which remember is LDR plus RDL. Let's go ahead and write down what all of these are. Our L is just x, and our R is e to the x squared times y. The derivative of L, dl, is really easy. It's just 1 because the derivative of x is 1. Let's focus on the derivative of the right part, the derivative of e to the x squared times y. Here we have to use chain rule because we have nested functions. We have the function x squared times y inside the function e to the x. So when we are using the chain rule, it's derivative of the outside times derivative of the inside. And the nice thing about e to any power, the derivative of the outside here is just e to the x squared times y. And now we multiply by the derivative of the inside. What's the derivative of x squared times y with respect to x? Well, we treat y like a constant, so we just get 2yx. Now that we have all this information, we can just plug it all in, and we'll end up with LDR is x times e to the x squared y times 2yx, plus RDL is ex squared y times 1. All right, and remember that the point was 1 comma natural log 2, so we plug in 1 for x and natural log of 2 for y, so we end up with 1 times e to the 1 squared times the natural log of 2, all times 2 times the natural log of 2 times 1. And then to that we'll add e to the 1 squared times the natural log of 2 times 1. This might seem like a lot, but believe me, it does simplify down a lot. All right. 1, we don't have to worry about that. E to the 1 squared times natural log of 2, well, that's just e to the natural log of 2. All times 2 times the natural log of 2 times 1 is just 2 natural log of 2. Plus e to the 1 squared natural log of 2 times 1 is just e to the natural log of 2. So what is e to the natural log of 2? Well, remember, e to some power and the natural log of that thing, they undo each other. So e to the natural log of 2 is just 2. So we end up with 2 times 2 natural log 2 plus 2. And that can simplify to be 4 times the natural log of 2 plus 2. All right, with that in mind, let's turn our attention to finding f of y. So remember, our original function is f of xy is f of xy equals x times e to the x squared y, and we want to find fy. Here, we don't have to do product rule, because remember, now we're treating x like a constant. So the derivative of f with respect to y is just x times the derivative with respect to y, the function e to the x squared y. Now here we do have to do chain rule because we have functions of outside and inside all combined together, but it's not too hard. It's just like last time. So we'll end up with x times e to the x squared y times the derivative of the inside. The derivative of x squared times y is just going to be x squared. So now we plug in our points 1 and natural log of 2, and what that will end up looking like is 1 times e to the 1 squared natural log of 2 times 1 squared, which is going to simplify down to be e times the natural log of 2, which is just 2.